All right, on page 17, let's set the scene. The senior talent show is scheduled to take place this afternoon. Michael Senator is in stats class practicing his act, bottle flipping. He tells his friends that the probability of successfully landing the water bottle right side up is 20%. Assume that each water bottle flip is independent. If he flips the bottle 10 times, how many do you expect to land right side up? How should we approach this problem? What kind of setting is this? Is this a binomial setting? Let's walk through it. What things do we need to check to see if it is a binomial setting? Bins. So let's see if we get bins. Is this binary? Think about it. How do we determine if it's binary? Two options. What are the two options for bottle flipping here? Yep. Lands right side up, or it doesn't land right side up. So is this a binary situation? Yes. Do we get independence? Yep. It says assume each water bottle flip is independent, so we're okay to get independence here. Do we have a fixed value for n? Read the question. What is n? 10. It said right there that he is flipping the bottle 10 times. Do we have the same probability of success each time? Yes, what is the probability of success? 20%. So is this a binomial setting? Yes. So let's calculate the probability then, given that this is a binomial setting. We want the expected value. What is the expected value when we're talking about random variables? That's the same thing as the mean. The expected value is the same thing as the mean. How do we calculate the mean for a binomial setting? N times P, yes. So what do we get if we do N times P? We get 2. 10 times 0.20, so 2 flips. If he's going to flip it 10 times, we expect 2 of them to land right side up. What's the probability that he makes exactly 2 flips? How do we calculate this? What would my probability notation look like? Let's start there. Probability x equals 2. Probability x equals 2. There's 2 different ways we could calculate this. What's one of the possible ways we could calculate the probability that he makes exactly 2 flips? Hey, dear, you look like you have an idea.
Like 2 times 20%, or 2 times 20% is 8 times 80%?
Close. Close, close, close. So we want to know the probability he makes exactly 2, so you've got 20%, and then you're timesing it by 2, and then adding that. But we want to know the probability that he makes 2 flips and doesn't land 8 of them. So what do I need to do with the probabilities? Multiply them together. And how do I take into account that we want him to make exactly 2 and miss exactly 8? Those would be exponents, yes. All right, so there's one other piece that has to go into this. Because if he's going to make exactly 2, are we guaranteed that it's the first 2 that he's going to make? Could it be the last 2? Could it be the first one and the last one? How many different ways are there to do this? How do I figure out how many different ways there are that he gets exactly 2 flips to land right side up? 10C2. Let's pop that into the calculator and see what we get. Now, we need to put a number in before we do that. So you need to put the 10 in first and then do what I showed you. So type in the 10 and then do that piece to get the C. Does anybody have an answer? 0.302 is what I got as well. There's another way that we could calculate this using the calculators that you guys grabbed to do this. What's the other way I could do this? Binom PDF. If I want the probability for just one specific situation, it's the PDF. And what kinds of things would we need to put in the binom PDF? Number of trials, which is 10, all right? And I need to label that. What else do I need to feed it? Probability of success, which is 0.2 or 0.20. I don't care if you put that last 0 on the end. And what else do we need? The x value, which in this case would be 2. I want you guys to pop that one into your calculator. And again, the app won't do the binom PDF, but the graphing calculators in the back will. So if you were using the app for the other one, go grab a graphing calculator from the back so that you can do this. When you type this in, you should get the same answer. All right. What's the probability that he makes less than 2 flips? What would my probability notation look like now? X is less than or equal to 2. Again, there's 2 different ways I could calculate this. What's one of the possible ways we could go about calculating the probability that he makes less than 2 flips? Binom CDF. Now, what's the deal with the binom CDF that we have to be careful about? If it's greater than, we have to subtract it from 1. But specifically, when I go to put in an x value into binom CDF, it's not just less than. It's always less than or equal to. But I don't want this to be or equal to 2. I want him to make less than 2 flips. So what are the options for less than 2 flips? 1 or 0. There's only 2 options there, right? So I want the probability that it's less than or equal to 1. Again, we have to do it like this because the calculator does not do just straight less than. It only does less than or equal to. You said we're going to do a binom CDF. What pieces of information do I need to feed into the calculator for a binom CDF? Trials, which is 10. What else? Probability of success, which is still 0.20. And then we have to give it what else? X, which on this one is, what is our X value this time? 1. Because remember, the X value is going to be a less than or equal to. When I say less than 2 flips, that means 0 or 1, so less than or equal to 1. Go ahead and pop that into your calculator and tell me what you get.
So how would I know when to use binom PDF and binom PDF?
That's a great question. Binom PDF is when I want X equal to something, no inequalities. I want the probability of one event. CDF is when I have a less than or equal to. I want the cumulative probability. I want it to take several probabilities and put them together. Does anybody have a value here? 0.376 if you round it to 3 places. I took mine out to 4 places, so I have 0.3758. But if you round it to 0.376, that's totally fine. I said there was another way to calculate this one. We can do binom CDF. Perfectly appropriate, as long as you label N, P, and X, and you have your inequalities. So you need to have your inequalities here in addition to having your labels. It's totally fine to just put it into the calculator at that point. We could do this one similar to this right here, only I don't want the probability that X is equal to 2. I want less than 2, which you said were, what were my options there? 1 or 0, right? So I could find the probability that X is equal to 1, the probability that X is equal to 0, and I could put those two together. Now, typically, I don't like to do a less than or equal to this way, because usually there's more than just 2 things that we would need to calculate, and that gets to be too much. My preference is binom CDF. But you should get the exact same answer, no matter which way you calculate this one out. Well, if the probability that he makes strictly less than 2 flips is 0.3758, how would I find the probability that he makes 2 or more? First of all, what would my probability notation look like? Probability that X is greater than or equal to 2, yes. Does my calculator do greater thans? No, it only does less than or equal to. So how do I handle a greater than situation? I'm going to subtract. We do 1 minus the probability that X is less than 2. Well, what is the probability that X is less than 2? What'd you say? 0.3758. So we're going to do 1 minus 0.3758. And that means we get what? 0.6242. So the probability that he lands 0 or one of these flips is about 37.5%-ish. The probability that he makes 2 or more flips is about 62.5%-ish. So far, so good? Just from looking at what we've been struggling with as a big group over the last couple days, one of the things I want to remind you of is when we're looking at situations like this, or like number 2, you want to always go in to check to see, is this a binomial setting? Is this a binomial setting? Because you are given a lot of the formulas on the formula page, but you have to know when to apply them, when to use them. So like number 1, we had to figure out first whether or not this was binomial, and then we knew how to find the expected value, n times p. So especially in this chapter, always check to see if something is binomial. Always check your bins. All right, let's scoot down the page. After the first 10 flips, Michael wants to do more, but his teacher is getting annoyed. This is about a real student, and I met this teacher, and she said he really was doing bottle flipping at the senior talent show. And he really was practicing for it during class, and he really was driving her absolutely nuts. But she was very funny about it. There's a YouTube video of it when he actually performed in the talent show. It's like a 10-second video because he landed the first one. But that's what started this whole thing, is this really happened in a stats teacher's class. Teacher's getting annoyed with all the noise and tells him he must stop flipping once the bottle lands right side up. So he can keep trying, but once he lands one right side up, he's got to stop and be done for the rest of the class period. What's the probability that he lands this on the very first try? What'd you say? 50%. Not 50%. What'd you say? Not 10%. We're getting closer, though. It's going to be in between 50 and 10%. If you look on the page, it actually tells you the answer. 20%. Because the probability of success is 20%. So the probability that he lands it right side up on the very first try, the probability that x equals 1 is 20%. 0.20. Find the probability that he fails on the first try and lands it on the second try. So something like this. How do we find the probability for an and? We multiply probabilities together, right? So what's the probability that he fails the first one? 0.80. What's the probability that he lands the second one? 0.20. So I'm going to take 0.80 times 0.20. We've got our first flip and our second flip. What is 0.80 times 0.20? 0.16. Find the probability that he fails the first 2 and lands it on the third try. What would this look like? Probability. Fails first 2, lands the third one. So now I have how many flips that we need to multiply the probabilities for? I have 3 total, right? Because he's flipping the bottle 3 times. He misses the first 2 and he lands the third one. What's the probability he misses the first one? 0.80. Misses the second one? 0.80. Lands the third one? 0.20. So we're going to take 0.80 times 0.80 times 0.20. What's this one come out to? 0.128. Find the probability that he fails the first 3 and lands it on the 4th try. What's this one going to look like? Tell me how to write it out. Probability fails first 3 and lands 4th. Okay, so what's my work going to look like? 0.80. Can you do it to the 3rd? Yes, you can. 0.80 to the 3rd, because we've got 3 failures. 0.20 to the 1st, because we have 1 success. So 0.80 times 0.80 times 0.80 times 0.20. What do we get? 0.1024. I want you to look at what's happening to our probabilities. The probability that he lands it the very first try, we said was what? 0.20. The probability he misses the first one but lands the second one was what? 0.16. Did the probability go up or down? Probability went down. Probability that he misses the first 2 and lands it on the 3rd one was what? 0.128. Did my probability go up or down? Down again. Probability that he misses the first 3 and lands it on the 4th one? 0.1024. Probability went up or down? Down again. So if I were to draw what this distribution looked like, my probability starts off like the highest it ever is 1 flip. And then probability that it takes him 2 flips to get the first success, it went down. The probability that it takes 3 flips to get the first success, it goes down. Goes down, goes down, goes down. How would you describe that shape? If it keeps going down each time? Skewed to the, where's the tail? On the right-hand side. This would be a skewed right distribution. All right, so there's a table down underneath number 8. We've already come up with a lot of the numbers that belong in that table. What's the probability lands it on the first try? 0.20. Second try? 0.16. Third try? 0.128. Fourth try? 0.1024. I want you guys to fill in the rest of this table. What's the probability it takes him until the 5th flip to land it? Sorry. Probability that it takes him until the 5th flip. He misses the first 4, but he lands the 5th one. 0.0819. What's the probability that he doesn't actually get one to land upright until the 6th flip? 0.0655. This kind of a pattern right here. Does anybody see what's happening each time we move along here? Yeah, it's being multiplied by 0.80 each time. So we have this pattern of repeated multiplication. Does anybody happen to remember from Algebra 2 what we call a sequence of numbers like that where you are multiplying by the same thing over and over and over? This is called a geometric sequence. It's okay. It's a real short unit in Algebra 2, and I know it's been a minute since you guys have had Algebra 2. This is called a geometric sequence. Oops, I need more room to write geometric. Do you guys remember at all hearing about a geometric sequence? There was an arithmetic sequence and a geometric sequence. Arithmetic was the one where it's repeated addition to get the next term. Geometric was where it was repeated multiplication to get the next term. Because of that, whenever we are looking at a situation until the first success, I'm going to repeat something over and over and over until I have my first success. We say it is a geometric distribution. As opposed to the binomial distribution. Binomial distribution, I just want to know, well, what's the chance that I see 2 successes or 5 successes or 10 successes in this group of trials? Geometric is always specifically, I'm going to do this thing over and over and over until I see my first success, and then I'm going to stop. So it's like I'm going to keep reaching into my bag of M&Ms until I get that first green one, and then I'm going to stop eating whatever, M&Ms, Skittles, whatever kind of candy we're looking at. So if it's 0.0655, and you guys already kind of found a shortcut for us back here, these are my failures, and I only have 1 success. Can you find the probability for me that it takes until the 10th try to get the first success? On the 10th flip, he gets his first success. If it takes until the 10th flip to see your first success, how many failures has he had to deal with? 9 failures. So what would this look like when you go to put it in the calculator? Yep, 0.8 to the 9th power times 0.20. Only 1 success in there, so 0.20 just happens the one time. But we've multiplied by 0.8, 0.8, 0.8, 9 different times for our 9 failures. What'd you guys get? 0.0268, so about a 2.5% probability that he fails the first 9 flips and then finally lands the 10th one. Let's come up with a generic rule that we can use for landing it on the kth flip. So the probability that x is equal to k in my geometric setting. Yes. Now, if I was looking at any general setting, where maybe I don't know what the probability is. What you said would be perfectly right as a general rule for this setting. If I didn't know what the probability is, my probability of success, we always use P to represent that, right? So how do we represent the probability of a failure then? P complement. How do we calculate P complement? What do you notice about the 0.2 and the 0.80? I didn't even have to ask you guys. It's 1 minus the probability of success, right? Remember, complementary numbers are always numbers that add up to 1. So when I'm looking at the complement, it would be 1 minus that. So 1 minus P to the power of K minus 1 times P, or you could say P to the first. Only one success. K minus 1 failures. Where K is the number of trials that we have. How many flips do you think it's going to take? How many flips would you expect it to take for the bottle to land right side up? Well, what's his probability of success? 20%. What is 20% as a fraction? What'd you say? 2 over 10. Can we reduce 2 over 10? 1 over 5. So I would expect 1 in the first 5 flips. So I expect that it's going to take 5 flips. The way we calculate the mean for a geometric scenario is 1 over the probability of success. If you do 1 divided by 0.2 on your calculator, you should get 5. All right. Couple of big ideas, and this is what we've been waiting on. We've practiced with binomial random variables for 3 days. This one is related to the binomial random variable. This is that last piece that we were waiting on so you guys could finish up your homework, is the geometric distribution. Geometric distribution is, geometric distribution see if I can get my thing to work now. Related to the binomial distribution. We still have a binary. There's a success or a failure. He either lands the bottle right side up or he doesn't. The difference is that we're going to take our number of trials. It's no longer fixed. It's trials until we see success. We still need to check our independence, and we still need the same probability of success each time. We're going to repeat the process until we see our first success. Even if it takes 100 tries, we're going to keep going. Keep going, keep going, until we see that success. The formula, which we just built, for a geometric distribution to find the probability that x is equal to some number, we do our probability of failure to the power of however many failures, times the probability of success. And you could even say the probability of success to the first power because we want exactly 1 success. But when we have an exponent of 1, like 2 to the first power is just 2. 5 to the first power is just 5. So you don't have to put the exponent of 1 up there, but you can. It doesn't make a difference. Geometric distributions are always skewed to the right. The highest probability, the highest single probability, not cumulative, but the highest single probability will always be that first try. After that, the probability is going to go down, 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 down. The center, the mean, or we could say the expected value, is 1 over the probability of success. And the variability, or our standard deviation, we calculate by doing the square root of 1 minus the probability of success. So the square root of the probability of failure divided by the probability of success. We have 6 questions down on the check your understanding. So why don't we take 7 minutes, a little bit more than a minute per question. I would like for you guys to try the check your understanding. We're going to take about 7 minutes. If it says nothing in here, so let's think about this situation. If it doesn't say anything about independence, let's put ourselves in this situation. Mason starts asking people for pencils. Is my willingness to say yes to Mason influenced by other people's willingness to say yes? Do you think a good-hearted person that always is willing to share stuff would be influenced by this? So I think it's probably okay for us to assume independence here. But you're right, that one is, it doesn't give you much to go on. Almost all of these situations, if we're being asked to calculate things from it, it doesn't say anything about independence. If we have no other way to check, say it's okay for us to ask for independence. Trials until success. Are we going to keep going until we see success? So this one is saying, what's the probability that it's exactly the third person he asks? This one is saying, by the time he gets around to asking the third person, so the first person might get a pencil, or the second person might get a pencil, or the third person might get a pencil. Any of those options would satisfy this one. Here, it has to be the third person. Here, it could be the first, or the second, or the third. So what you then you need to find the probabilities for each of them and add them together. Okay. Does the random variable y, in this case y is equal to the number of students that Mason asks until he finds someone who will give him a pencil, is this a geometric distribution? Yes. We need to check bins, or I don't know if you guys noticed, but they had a T for trials until success. So I can think of this as bins or bits. Are we binary? Yes. What's success look like? Getting a pencil. Failure? Not getting a pencil. Independence. We're going to go ahead and assume that this is independent. That a big-hearted person that's usually willing to share with other people is not going to be affected if everybody else says no, and a person that would be inclined to not share their belongings ever is not going to be influenced by other people saying yes or no. So we're going to assume that this is independent. Number of trials. We don't know, but we do know we're going to go until the first success. That's what I'm looking for geometric. Are we going to go until the first success? Same probability of success each time. Do we have that? What is that? 0.15. Got that right up here. So is this a geometric distribution? Yes. Yes, it is a geometric distribution. And I accidentally wrote geometry distribution. All right, what's the probability that the third person asked is the first one that finally gives him a pencil? How do I calculate this? Probability y equals 3. 0.85 squared times 0.15. And that gives us what? 0.108 or 1084 if you take it out to 4 places. Yes.
What if I wrote it differently than that?
For which part?
I'll put it probability doesn't receive first two and then receives the third. Would that be wrong?
Sorry, one more time.
Probability like doesn't receive the first two and then receives the third.
Oh, you're talking about this notation right here.
Yeah.
Oh, yeah, that's okay to write it that way. Yes. So do you guys remember how there's a shortcut on the calculator for binomial? We have a shortcut on the calculator for geometric also. I'm going to show you where that is. Grab your graphing calculators. On the app, again, this is a paid feature, unfortunately, so you need one of the calculators from the back. All right. We're going to go to second and vars, which is the same place that we go to for binomial. You're going to have to scroll down even farther than before. There's my binomial PDF and CDF. And way down here, after inverse binomial and Poisson, we finally get to geometric. If I want the probability that x equals 3, I want a single probability. That's the PDF. So I'm going to click on that. It only wants 2 pieces of information from me. What's it want? Probability of success, which in this case is 0.15. And then we want our x value. What are we going to put in for x? 3. Then we're going to paste that in. And we're going to hit enter. 0.10084 if I round it to 4 decimal places. Could do a Geomet PDF feeding it P, probability of success, and X, and we get the exact same thing. The difference between question 2 and question 3. Question 2, I want to know what's the probability that it takes exactly until the third person. Question number 3, I'd be okay if he got it with the first person or the second person or the third person. So what do I need to do with my probabilities here? We're going to add up these different probabilities. So what's the probability that he gets it from the first person? 0.15. Probability that he gets it from the second person, how do I calculate that? 0.85 times 0.15. And the third person? 0.85 squared times 0.15. What do you get when you add all of those up? 0.386 or 3859, depending on where you rounded. If you rounded out to 3 decimal places, that's always fine. This is another one where we have a shortcut on the calculator. Since I want a less than or equal to, what do you think I could use here? I can use Geomet CDF here. We have to give it 2 pieces of information again. Probability and our x value. I'm going to switch over to my graphing calculator and we're going to pull this up. All right, so second and vars. Scroll, 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 scroll. Ooh, second and vars. Take me back here. Scroll down until you see geometric CDF. It's option G way down here. Probability of success is 0.15. The x value on a CDF is always less than or equal to. Remember that when you're working on these on your homework. And then we're going to paste that in and hit enter. 0.3859 or 0.386, depending on where you round. How many people should Mason expect to ask before getting a pencil? When I ask for the expected value, that's the same thing as what? The mean. How do we calculate the mean for geometric? 1 divided by the probability of success, which in this case, the probability of success was 0.15. What do you get when you do 1 divided by 0.15? 6.6 repeating, or 6.67 if I round it out. So he should expect to ask between 6 and 7 people. Should Mason be surprised if he doesn't receive a pencil until he asked at least 10 people? So probability that X is greater than or equal to 10. Can I do greater than or equal to on the calculator? No, I can only do less than or equal to. Well, if I want to know the probability of greater than or equal to, what do I need to do? Subtract. We do 1 minus. This would be 1 minus the probability that X is less than or equal to what? I want the or equal to go with the greater than, right? What would be the opposite of 10 or more? 9 or less. The opposite of 10 or more would be 9 or less. So the probability that X is less than or equal to 9. So I'm going to cheat, and I'm going to use my geometric CDF. That's not cheating, by the way. But it is a lot faster than doing the probability of 1 plus the probability of 2 plus the probability of 3 plus the probability of 4 all the way up to 9, like we could do on the other problem. And this is what I got. 1 minus, when I did just geometric CDF, with P being 0.15 and X being 9, I got 0.7684, so I do 1 minus 0.7684, which comes back with what? 0.2316. So should he be surprised if he has to ask 10 or more people? No. What's our cutoff? 5%. This is more than 5%, so it is not an unlikely outcome. Very last one, number 6. We have the formula for standard deviation up at the top of the page. I would like for you to calculate the standard deviation. What do we need to do to calculate standard deviation here? Square root of 1 minus P divided by P. So square root of 1 minus 0.15 over 0.15. What'd you get? 6.1 something something. I rounded it to 6.15. Homework, if you guys remember yesterday, I told you I'm going to give you one extra day on it, which actually gives you the whole weekend as well. It's not due tomorrow like originally stated. Tomorrow, we're going to practice with random variables, binomial, and geometric distributions. So we're just going to practice what we've done in this chapter. We are all the way done with new material. There's nothing new coming before the test. Tomorrow, we'll spend some time reviewing. You should end up with a little bit of homework time or time to ask me questions about stuff off the homework if you get stuck on it. Monday, we'll grade your homework and we'll do some multiple choice practice. Tuesday, we'll do some free response question practice. Wednesday, I'll take questions over the paper test review that you guys will get tomorrow. You can pick it up tomorrow if you want to, but if you're afraid you're going to get it confused with your homework, you can wait until Monday to pick it up. And then Thursday next week will be your test. So a week from today.